All right, welcome back to the deep dive. Today we're diving into a world where the future is a mystery, and we have to make decisions on the fly.
Ah, yes, the realm of online algorithms. Right.
You got it. We're talking about those algorithms that have to process information as it comes in without knowing what's coming next.
So it's like navigating a maze in the dark.
Exactly. A perfect analogy. You
Yeah.
only know the next step, not the whole path.
Quite a challenge for any algorithm.
It is, and it makes you think about how different this is from the traditional offline algorithms.
Oh, absolutely. In offline algorithms, you've got the whole picture from the start. You can plan everything out in advance.
It's like having a map of the maze before you even enter. But with online algorithms, you're making decisions with incomplete information.
Like figuring out whether to bring an umbrella when you see a few clouds in the sky. You have to decide based on what you know right now.
Precisely. You can't wait until later to see if it actually rained. You know, it's funny, we might not realize it, but we're already pretty familiar with this idea of online processing.
True. Think about how your computer handles data. When you insert an item into a list, delete something, or search for it, those operations are often online. You're dealing with the data as it comes in right then and there.
Oh, I see what you mean. The computer doesn't know what data you're going to throw at it next. It just has to handle each request as it arrives.
Exactly. And the way we analyze the efficiency of those operations over time by looking at the average cost that hints at this idea of step-by-step processing.
So online algorithms are a lot more relevant than we might initially think,
Absolutely. And in today's world, they're becoming more crucial than ever.
especially in those applications where the future is just, well, unpredictable.
Take stock trading, for instance. Algorithms have to analyze market data and make decisions in a split second. They can't afford to wait and see what happens tomorrow.
High stakes and no time for second guessing.
Right. And then there's the problem of scheduling jobs on a computer. New tasks are constantly popping up. The system has to decide how to allocate resources without knowing what else is coming down the pipeline.
So it's about making the most efficient use of resources in real time.
Precisely. And it's not just limited to the digital world.
You're right. Businesses face similar challenges with inventory management.
Exactly. They have to decide when to order more supplies without knowing for sure what demand will look like in the future.
That sounds like a logistical nightmare.
It can be. And think about ride-hailing services. They need to match riders with drivers as requests come in without a perfect overview of the whole day.
It's fascinating how these online algorithms are working behind the scenes in so many different areas.
They truly are. And the big question, of course, is how do you design an algorithm when you don't have a crystal ball?
Yeah. How do you make good decisions when you're essentially operating in the dark?
Well, one approach is to try and model the future. You can use probability, queuing theory, even machine learning to predict what might happen next. It's like using historical weather data to guess if you need an umbrella today.
So you're trying to anticipate the future based on past patterns.
Right. But the approach that we're going to focus on today is a bit more conservative.
Oh, really? How so?
Instead of trying to predict the future, this approach focuses on guaranteeing a certain level of performance no matter what the future holds.
So it's about being prepared for the worst case scenario.
Exactly. And that's where this concept of competitive analysis comes in.
Competitive analysis. So what are we competing against?
We're comparing our online algorithm to a hypothetical offline algorithm.
Okay, I'm listening. What makes this offline algorithm so special?
This offline algorithm has perfect foresight. It knows the entire sequence of inputs in advance. It's like having a time traveler whisper all the future stock prices in your ear.
Ah, so it's an unfair competition. Our online algorithm is going up against an all-knowing opponent.
You could say that, but it's a useful benchmark. And for problems where we're trying to minimize something like cost or time, we use something called the competitive ratio.
The competitive ratio, what's that?
It essentially measures how much worse our online algorithm performs compared to this all-knowing offline algorithm in the worst-case scenario.
So it's a measure of how well our algorithm can handle the unexpected.
Precisely. And ideally, we want to get that competitive ratio as close to 1 as possible.
Meaning our online algorithm performs almost as well as the algorithm that knew the future all along.
Exactly. That's the ultimate goal.
Okay, I'm starting to see the bigger picture here. But can you give me a concrete example?
Of course. Let's talk about elevators. Imagine you're trying to decide whether to wait for the elevator or take the stairs.
A classic dilemma. We've all been there.
Right. So let's say it takes a gay minutes to climb Seoul floors. The elevator, on the other hand, takes just 1 minute to go up.
Sounds much faster. But there's a catch, right?
There is. The waiting time for the elevator is unpredictable. It could arrive immediately or it could take a while. Let's say the maximum waiting time is B1 minute.
So you never know how long you'll be stuck waiting.
Now, if we had our all-knowing offline algorithm, it would know exactly when the elevator was going to arrive. If the waiting time is less than K1 minutes, it would wait for the elevator. Otherwise, it would take the stairs.
So the offline algorithm always makes the optimal choice.
Exactly. But we, mere mortals, don't have that luxury.
So what's a simple online strategy we could use?
Well, we could always take the stairs.
Seems straightforward enough.
But think about the worst-case scenario. What if the elevator arrives right as you start climbing the stairs?
Oh, I see. You'd spend K minutes on the stairs while the offline algorithm would just hop down the elevator and reach the top in a minute.
Exactly. That means the competitive ratio of this always take the stairs strategy could be as high as K.
So not very efficient if you're going up many floors.
Right. And the opposite strategy, always waiting for the elevator, isn't much better.
What's the worst case scenario there?
Imagine the elevator takes the maximum possible time, B1 minutes, to arrive. You'd be waiting forever, while the offline algorithm, knowing the elevator was going to be so slow, would have already reached the top via the stairs.
So both of these simple strategies have pretty bad competitive ratios in the worst case.
They do. But don't worry, there's a better way.
Tell me more.
It's called the hedging strategy.
Hedging. What's that all about?
The idea is to wait for a certain amount of time. Let's say I like minutes, which is the time it takes to climb the stairs. If the elevator arrives within that time, you take it.
So you're giving the elevator a chance to prove it's not going to be terribly slow.
Exactly. But if it doesn't arrive within those alley minutes, you give up and take the stairs.
So you're limiting your potential losses by setting a time limit.
Right. And the beautiful thing is that no matter what the actual waiting time is, the competitive ratio of this hedging strategy is at most 2.
Really? How does that work?
Well, let's break it down. If the elevator arrives quickly, say in M minutes, which is less than K1, then the optimal offline strategy would have waited for the elevator, taking M plus 1 minutes in total. Our hedging strategy, in this case, would take at most K plus 1 minutes.
So the ratio between our strategy and the optimal one would be K plus 1, ME plus 1, which is at most 2.
Precisely. And if the elevator is slow, taking more than M minutes to arrive, then the optimal strategy would have been to take the stairs, taking A minutes. Our hedging strategy would also take AK minutes to reach the stairs, and then another A minutes to climb them, for a total of 2K minutes.
So the ratio is 2KK, which is again 2.
Exactly. So, regardless of the actual waiting time, the hedging strategy guarantees that we'll never perform more than twice as poorly as the optimal offline algorithm.
That's impressive. A simple strategy with a guaranteed level of performance.
It really highlights the power of competitive analysis. We found a way to deal with the uncertainty of the elevator arrival time without trying to predict the future.
It's all about mitigating the worst case scenario.
Precisely. Now let's move on to another interesting problem where online algorithms shine. Maintaining a search list.
Search list, like a library catalog.
Exactly. Imagine you have a list of items, and you need to search for them repeatedly. The goal is to organize this list in a way that makes future searches as efficient as possible.
So you want the most frequently searched items to be easily accessible.
Exactly. But here's the challenge. You don't know in advance which items will be searched for most often.
So you can't just arrange the list once and be done with it.
Right. If you did that, you could end up with a static ordering that performs terribly if the search patterns change over time.
It's like organizing your bookshelf based on what you thought you'd read most, only to find yourself constantly reaching for books on the bottom shelf.
A perfect analogy. And in the worst case scenario where you always need the item at the very end of the list, searching would be extremely inefficient.
So how do online algorithms tackle this problem?
One common strategy is called the move to front algorithm, or MTF for short.
MTF, how does that work?
It's surprisingly simple. Every time you search for an item and find it, you move it to the front of the list.
So if you're searching for the same item repeatedly, it'll always be at the top.
Exactly. It's like keeping your most recently used book on your desk for easy access.
Makes sense. So what's the cost of a single search using MTF?
Well, let's say the item we're looking for is at position R in the list. We first have to search through R elements to find it. Then we move it to the front.
Moving it to the front involves some relinking if it's a doubly linked list.
Right, which takes about R1 steps in the worst case. So the total cost for that search is roughly 2 or 1.
Okay, but how do we know if MTF is a good strategy overall?
To analyze its performance, we compare it to a hypothetical optimal offline algorithm called 4C.
4C. Another all-knowing algorithm.
Exactly. 4C knows the entire sequence of searches in advance. So after each search, it can rearrange the list in the absolute best possible way to minimize the cost of all future searches.
It's like having a cheat sheet for the search list problem.
You could say that. Now, to compare MTF with 4C, we use this interesting concept of inversions.
Inversions. I'm intrigued. What are those?
An inversion occurs when a pair of elements has a different relative order in the list maintained by MTF compared to the list maintained by 4C.
So if element A comes before element B in MTS list, but B comes before A in 4C's list, that's an inversion.
Precisely. And the inversion count is simply the total number of such pairs of elements that are in a different order in the two lists.
So it's a measure of how much the two lists differ in their arrangement.
Right. And the chapter presents a theorem about MTF's performance in relation to this inversion count.
What does the theorem say?
Theorem 27.1 states that MTF has a competitive ratio of 4.
A competitive ratio of 4. What does that mean?
It means that in the worst-case scenario, MTF might take up to 4 times as long as 4C to perform the same sequence of searches.
So not perfect, but still a decent guarantee considering we have no knowledge of the future searches.
Exactly. MTF gives us a bounded competitive ratio, which is much better than the potentially unbounded cost we could have with a static ordering.
So it's a robust strategy that adapts to the observed search patterns without needing any prior knowledge.
Absolutely.
Yeah.
Now, let's shift gears to another critical area where online algorithms are essential. Caching.
Caching. You mean like the cache in my computer's memory?
Precisely. You have a small, fast cache that stores frequently used data from a much larger, slower main memory. When your processor needs a piece of data, it first checks the cache. If it's there, it's a cache hit, which is fast.
But if it's not there, that's a cache miss.
Right. And in that case, the system has to go fetch the data from the main memory, which takes much longer.
And the cache has limited space. So when it's full and you need to bring in new data, you have to decide which block of existing data to evict to make room.
And that's where online algorithms come in. The decision of which block to evict is an online problem. You don't know what data will be needed next.
So you have to make the best decision based on the history of requests.
Exactly. And the chapter discusses several different online caching policies, which are essentially rules that dictate which block to evict.
Like what?
Well, there's first in, first out, or FIFO.
FIFO. That sounds straightforward.
It is. FIFO evicts the block that's been in the cache for the longest time.
So the oldest one goes out. Simple.
Then there's last in, first out, or LIFO.
LIFO. So you evict the most recently accessed block.
Exactly. Counterintuitive, but that's how LIFO works.
Okay. What other policies are there?
We have least recently used, or LRU, which evicts the block that hasn't been accessed for the longest time.
So LRU tries to keep the most recently used data in the cache.
Right. And finally, there's least frequently used, or LFU, which evicts the block that's been accessed the fewest times.
It's all about trying to predict which data is most likely to be needed in the future.
Right. And to evaluate these policies, we use competitive analysis.
So how do these policies stack up against the optimal offline algorithm?
Well, LIFO, unfortunately, has an unbounded competitive ratio.
Unbounded, what does that mean?
It means that in the worst case, LIFO could perform arbitrarily badly compared to the optimal offline algorithm. And surprisingly, LFU also has an unbounded competitive ratio.
Wow, that's unexpected. You'd think tracking how frequently data is used would lead to better performance.
It seems intuitive, but in the worst-case scenario, both LIFO and LFU can be pretty terrible.
What about LRU and FIFO? How do they fare?
Both LRU and FIFO have a competitive ratio of OK, where pay is the size of the cache.
So their performance is bounded, but it still depends on the size of the cache.
Right. And it turns out that this is the best we can do with any deterministic online caching algorithm.
You mean there's a lower bound?
There is. Theorem 27.4 states that any deterministic online caching algorithm must have a competitive ratio of at least omega k.
So LRU and FIFO are essentially as good as it gets in terms of worst-case performance.
Precisely. But what if we introduce randomness?
Randomness, you mean randomized caching algorithms?
Exactly. Instead of following a fixed rule, these algorithms make probabilistic choices about which block to evict.
So they introduce an element of chance into the decision-making process.
Right. And when we analyze randomized algorithms, we need to consider the type of adversary we're competing against.
What kind of adversary are we talking about?
We usually analyze them against an oblivious adversary.
Oblivious, what does that mean?
It means the adversary doesn't know the random choices our algorithm will make in advance.
So it's a more realistic model of a real-world situation where the future is truly unknown.
Exactly. And one example of a randomized caching algorithm is the randomized marking algorithm.
Randomized marking, how does that work?
It's quite clever, actually. It maintains a mark bit for each block in the cache. Initially, all blocks are unmarked. When a requested block is found in the cache, we mark it.
So marking indicates recent use.
Right. When there's a cache miss, we first check if all the blocks are marked. If they are, we unmark them all. Then we randomly choose an unmarked block to evict and bring in the new block, marking it.
So the randomness comes in when choosing which unmarked block to evict.
Precisely. And this random element leads to a significant improvement in performance.
Really? How much better is it?
Randomized marking has an expected competitive ratio of O log k.
Log K. That's much better than the linear K we had with deterministic algorithms.
It is. A logarithmic competitive ratio means that the performance degrades much more slowly as the cache size increases.
So randomness can be a powerful tool when dealing with uncertainty.
It certainly can. It allows us to overcome the limitations of deterministic approaches.
This has been a fascinating journey into the world of online algorithms. Before we wrap up, the chapter provides a glossary of terms, which I think is a great way to solidify our understanding.
Absolutely. Let's go through them.
We've talked about online algorithms and offline algorithms, competitive analysis, and the competitive ratio. We looked at specific algorithms like move to front, its optimal counterpart for C, and the concept of inversions.
We also explored online caching, cache hits and misses, and different caching policies like FIFO, LIFO, LRU, and LFU.
And we touched upon the concept of oblivious adversaries and randomized algorithms like randomized marking.
Understanding these terms really lays the foundation for anyone wanting to dive deeper into this field.
So, to summarize, we explored the fascinating world of online algorithms, those clever strategies that navigate problems when the future is uncertain. We saw how they differ from offline algorithms and why they're so important in a vast range of modern applications. We then delved into competitive analysis, a framework for evaluating how well these algorithms perform against an all-knowing adversary.
And we looked at concrete examples, from the simple elevator problem to the more complex challenges of managing a search list in a cache. We saw how different online strategies perform and how randomness can be a powerful tool for overcoming limitations.
And perhaps the most important takeaway is that competitive analysis provides a way to design algorithms with provable performance guarantees, even when we're facing complete uncertainty about the future.
It's about creating algorithms that can adapt and perform reasonably well in any situation.
Now, here's a final thought to ponder. Think about other situations in your daily life where you have to make decisions without complete information. Maybe it's choosing a route to avoid traffic based on real-time updates, or deciding how to invest your money without knowing how the market will perform.
Interesting example.
How might the principles of competitive analysis apply to those situations? Could you identify a hedging strategy to limit your potential downsides, even if it doesn't guarantee the absolute best outcome?
That's a thought-provoking question. It highlights how these seemingly abstract concepts from computer science actually have deep connections to the way we make decisions in our everyday lives.
We're constantly navigating uncertainty, trying to make the best choices with the information we have.
And perhaps understanding the principles of online algorithms can help us become better decision makers in all aspects of our lives.
Well, that concludes our deep dive into online algorithms and competitive analysis as presented in this chapter. We've covered all the main ideas, definitions, examples, and theoretical results.
And hopefully we've sparked some curiosity in our listeners about this fascinating and increasingly relevant field.
Thanks for joining us, and we'll see you next time on The Deep Dive.